I got this registry setting for you. I got this registry tweak for you, boy. This one's going to knock your socks off. Oh my God, you'll never have another microstutter. You just wait. I got the secret sauce for you. So, this Greek poem started with a video about the NVIDIA drivers and talking about NVIDIA drivers and how people were complaining about them. And I had this bright idea that I could replicate some of the issues that people noticed after the driver releases, particularly concerning multi-monitor setups in the Vulkan API with microstuttering and visual glitches that appeared in those configurations. And I talked about APIs, I talked about drivers, and then I thought maybe I would create some benchmarks with some graphic settings in certain configurations that probably made no sense for real-world application, but could be useful to test that driver API interaction. I wasn't able to replicate those issues. I didn't have enough knowledge to test APIs. As I mentioned, you can roll back a driver, but you can't roll back an API. But I did introduce some microstuttering, which I thought was very interesting, simply by manipulating those graphic settings. And that got me thinking about microstuttering. Made a video about microstuttering, which ended up being more of an explanation of what microstuttering is and what frametime spikes are and what frametimes are. And that led me to this video where I'm going to share how to solve the microstuttering issues, how to stabilize your frametimes. Let me be clear about what this video is not. We are going to be talking about some BIOS settings, but this is not an optimization and tuning guide per se. You might pick up some pointers there, but that's not what this video is. Also, I have an Intel system, 14900K. I know a lot of people use AMD. I haven't played around with the latest generation of X3D chips. Know that what I'm explaining here are concepts. We are going to get into the nitty gritty. We are going to solve frametime spikes, microstuttering. I'm going to tell you what the most important setting is to resolve those issues, and that will be true generally, no matter what you're running. Okay, so understand that this is not an optimization and tuning guide. This is not something that is Intel has to be Intel specific. This is information that is going to apply to anyone, all you gamers out there who are trying to eliminate your microstutters. So first things first, I have to share my benchmark results, and I'm just going to go through them and tell you exactly what I did and exactly what the resolution was, and then we're going to get into the meat and potatoes. The meat and potatoes aren't the benchmarks. I had to run them to prove what I wanted to prove, to discover what I wanted to discover, but that's not the meat and potatoes here. So we're talking about a very, very small test suite, only 4 games. The Talos Principle, Metro Exodus Enhanced Edition, Red Dead Redemption 2, and a weird one, Detroit Become Human. Now, I picked these games because they were different from each other, and they gave me a chance to test the things that I wanted to test. Of these 4 games, we have a number of different configurations and a number of different test scenarios. I didn't have time for a gigantic suite of games. I kept it small, but you're going to see why, because we had a lot of different configurations. So the idea was simple. The first idea was to try to introduce microstuttering in a stock system setting. That is Intel optimized default. In my case, Intel optimized defaults and nothing else except for enabling XMP. Why? Well, because when people build their PC, they're going to pop their RAM in and they're going to enable XMP, and 99% of them, that's all they're going to do. Now, hopefully that my audience for this podcast, my viewers, will not be among those people who all they do is enable XMP. Hopefully you guys have a little bit of tolerance to get up there and play around a bit with your hardware. But most people are just going to enable XMP, and that's as much as they're ever going to get into the BIOS. So we have an Intel optimized default configuration where everything is stock, not just the CPU, also the GPU. My undervolt was removed for this testing, for all of this testing. We stuck with one NVIDIA driver that was 576.88. There have since been more releases. I updated later, but not for these core benchmark results. I did some other testing where I did update the graphics driver. But the core benchmark results, I wanted to maintain consistency, so we used NVIDIA driver 576.88 for these 4 games. We tested multiple APIs for these 4 games when the game gave us that option. So Talos Principle gives us the option for DirectX 11 and Vulkan, and there is a beta DX12, but I didn't test that one. Metro Exodus Enhanced Edition is DirectX 12 only. Red Dead Redemption 2 gives us the option to run in Vulkan or DirectX 12. And we did both. And Detroit Become Human is only Vulkan. And of those different APIs and APIs configurations, API selections per game, we tested 4 different configurations. The first configuration is just stock, as I explained. Intel optimized defaults with merely XMP enabled. The second configuration was my initial optimization and tune. So before I started this project, when I built my PC, I tuned and optimized, and it's not a hardcore overclock. It's not a very stressful optimization. For example, my RAM is XMP 7800. My system is running 7800 megahertz. All I did was adjust the timings and subtimings, all right, and some of the voltages. So that was an initial optimization. The next set of benchmarks for all of those APIs, for each of those 4 games, was to try to rebuild that optimization to dial in on the specific BIOS tuning that most affects frame times and is best able to eliminate microstuttering. So after working through the Intel optimized default configuration with simply XMP enabled and optimizing it, beginning to optimize it, adjusting some voltages, and then eventually we arrived at the refresh timings. Those are tRFC and tREFI. And there are other refresh timings in the BIOS as well that you could adjust, but those were the important ones. Once I discovered how important tRFC was, I stopped tuning. I ran the benchmarks immediately at that point. I ran the benchmarks after every adjustment. And then after making the tRFC adjustment in the BIOS, I ran the benchmarks again, where I saw some very, very interesting results. And I knew that I was on the path. I knew that I was about to discover the critical timings that could stabilize frame times and eliminate microstutters. And I ran the benchmarks after adjusting tRFC, and then I went and adjusted tREFI, and then I ran the benchmarks after tREFI, and the results were dramatic. So first of all, quick note about the graphics settings. There's nothing extraordinary to note here. Basically, where DLSS was an option, it was off. It was left off. Where ray tracing was an option, it was left off. The graphics settings were tuned to approach native resolution as closely as possible. This is the set of benchmarks I'm going to show you right now running on this configuration. Intel optimized defaults plus XMP only. All stock settings except for XMP enabled at 7800 megahertz. This is a 14900K RTX 5090 Zotac solid OC, 14900K delidded DirectI water blocked, RAM water blocked, everything's water blocked. All right, these are the stock settings, just XMP enabled. And what you have here is the Talos principle. I use this game because I wanted something that was not very graphically demanding, because I wanted to see average FPS go up. I wanted to monitor that as well as 1% lows and see how optimized the different engines were for these various configurations. You're seeing a 14.82% delta as percentage of average FPS. That is very good. And an average frame rate of around 240. That makes lows of about 200. That's in DirectX 11 stock. When I shift over to Vulkan for the same game, I see a much higher delta, this time 30. So you can see how big that green part here is on the bar graph. So now we're going to go to Metro Exodus Enhanced Edition. Again, this is all with just Intel optimized defaults and XMP enabled. Delta very high, 37% for Metro Exodus, and average FPS of around 140. Metro Exodus, we only ran one in the stock part of these benchmarks because it's only available in DirectX 12. Red Dead Redemption 2 in Vulkan at stock settings, close to 30% delta as percentage of average FPS, and about 150 in the average frame rates. Same game, DirectX 12, about 40%, just about the same, only slightly lower FPS, around 135 on average. Now, this next game is Detroit Become Human. This is a strange game because if you ever played this game, you're basically playing in a cutscene. So it's very, very difficult to get these 1% lows down because of all the texture switching between the cutscenes and the parts that you're playing. It's a very interesting game, but actually quite smooth. There's that initial pop when you exit a cutscene, but no, I didn't observe any microstutters in the tuned configuration here. So we're getting, but this is not the tuned configuration. This is just the stock one. We're getting 47%, which is very, very high. But again, this is a strange game. So you're basically playing a cutscene. It's an excellent game, by the way. So those are your stock. Now let's review the next setting. We're going to compare those results to the optimized setting. So here we have the optimized. This is the first one that I tuned, right? So my initial tuning. It's right here. 14900K locked at 5.7 gigahertz and 4.3 gigahertz on the P&E cores respectively, with load line calibration set to level 7 and a 0.5 volt negative offset. This idles at around 1.385 volts and throttles down no lower than 1.3 volts. So very, very good delta there. 5090 undervolted at 0.975 volts, power max to 104%, curve flattened at 2800 megahertz. RAM at 7800 megahertz, tRFC2 at 470, tRFC at 370. I'm going to get into these timings later. We're going to explain those in detail. tREFI at 8000, timings of 36, 46, 46, 46, 125, as well as several other subtiming adjustments. DRAM VDD and DRAM VDDQ at 1.48 volts apiece. Again, I'm going to explain those timings as well. So let's get into that. Again, Talos principle. And we actually got a little bit worse. So in the DirectX 11 at stock, we were at about a 15% delta, very small green bar there. And in the DirectX 11 benchmark for this game in the optimized configuration, that is with a little bit of tuning and optimization, system tuning and optimization, we actually have a slightly worse delta, 22%. But remember why I said I wanted to test this game? Because it's not very graphically demanding, and I wanted to see how average FPS responded, and look where we are. We're over 350, 375 average FPS in this game at this configuration with the original tune versus only 236 stock. When we switch over to Vulkan, we're observing a dramatic decline in the delta. Vulkan really responded well to my initial optimization and tuning. Average FPS about the same, right around 360, and delta's only 13% compared to the stock Vulkan in the Talos principles 30%. But Vulkan again pushes those frame rates way up. So 350 in the stock, 360 in the optimized, and in DX11 only 230. And then 375 when DX11 was all optimized in this game. Metro Exodus Enhanced Edition in DX12, and this was dramatic. So this is how a game with a lot of draw calls and therefore very sensitive to a lot of read-write operations will perform under an optimized and tuned configuration. Let's go back to the stock DX12, 37% delta as percentage of average FPS. 141 average frame rate, 1% lows, 88. And then you do a little bit of tuning, and what do you wind up with? 150 in the frame rates, average FPS, and look at that delta. Look at that green, you barely see it. 5.56%. Almost no difference whatsoever between 1% lows and average frame rate. It is impossible to have a microstutter right here. Impossible. Switching over to Red Dead Redemption, in the Vulkan settings, in the initial tune, about 150 average FPS, about a 30% delta. And this is in Vulkan. Compared to stock, right around the same. A little improvement, not much difference. Right around 150 frame rate, close to 30% delta. So we haven't significantly smoothed the experience there. In DirectX 12, same game. Still hovering right around a 30% delta with around 150 as your frame rate. Then you go over here into Red Dead in the DX12 stock configuration, slightly worse. So we did improve things a little bit. We're getting closer to 40% as a delta with 135 average FPS. And last, Detroit Become Human. Again, I explained this is a weird game. And we did reduce our delta a little bit. This goes down to 42.5%, about 225 average FPS. And in the stock configuration, slightly higher FPS, slightly worse delta. So that's what we have as a comparison between the stock configuration and the average and the Intel optimized default configuration and the optimized and tuned configuration. So now we get into something a little bit different. So the idea here for the benchmarks was this. We would start off with the defaults, then I would switch my BIOS profile back to my original tune, and then we would do benchmarks on all those APIs for those games on those two different configurations. And we'd see the differences. As you saw here, we got some anomalies, all right? And then next, at that point, to dial in, we saw mostly an improvement, but we got some anomalies. And then to dial in exactly which settings are most responsible for the improvement of frame times and thus the elimination of microstuttering, we then decided to rebuild that initial tune. So going from Intel optimized defaults, we started to make that configuration closer to the original tune. And then eventually I'm going to surpass it, hopefully. But so again, in the process of making it more like the original tune, we adjusted some voltages, VDD, VDDQ on both CPU and DRAM. We locked our cores, and we then started to play with some very, very important subtimings, one of which being tRFC. Before I get into tRFC, I want to explain tREFI. tREFI we changed later. tREFI we changed on the fourth pass with the fourth configuration. My cat's got the zoomies. On the fourth configuration, we played with tREFI. Before that, we did tRFC, but I want to talk about tREFI first. And I want to talk about it first because you'll see. Once you explain this particular timing, it positions you to understand everything else because of all the things that you must understand to have a comprehensive understanding of what tREFI does. So let's talk about tREFI first, and then I'll get back to these benchmarks. Okay, so an understanding of tREFI is absolutely critical to understanding how to tune and optimize and overclock your system. You go onto forums, you go onto Reddit, you look on YouTube or whatever, everybody's going to tell you how to just plug in a number, but you won't know what that number is doing. So here at Wunyo Tech, we explain things, okay? It's important to understand things. So let's review tREFI, okay? So what is tREFI? What is it actually doing, okay? So first, to understand this, we got to understand bit lines and word lines and what they're actually doing. So what happens is you've got your bank, okay? Your bank is a 2D array of storage cells, DRAM cells. It exists on a die. So here's your die. And that die is, if it's an 8-bit cell, you've got rows, and you've got columns, right? And so these rows and columns, your rows are your word lines, and your columns are your bit lines. Okay? So you've got, in an 8-bit cell, typical cell, you would have 65,536 rows. And you would have 8,192 columns. Okay? Your blue is your word lines, your green is your bit lines. Now let's look at an individual cell. So an individual cell might look something like this. So you have your transistor, which is connected to your capacitor. All right? And this is a DRAM memory cell. Now, your word lines, let's keep our color codes here. Your word lines are going in rows, so it's connecting these cells this way. And your bit lines are going vertically. When a row is asserted, when a word line is asserted, all of the capacitors are read on that specific word line. Can't read all of the capacitors. It doesn't read all of them, because then you'll have voltage coming across, going into your bit line, colliding with the transistors and capacitors up here, and voltages colliding across your bit line. So only the capacitors associated with that word line that is being asserted are being read. So what's happening here, let's say that this, I'm filling this in with red here, because what I'm trying to represent here is that this capacitor is holding 1 volt. 1 volt. But at this point, the word line is asserted, which means that this capacitor, or rather this transistor, is closed. This voltage then is now flowing from the capacitor over to the bit line. Now, the first step in reading, writing, and refreshing, and that's what we're really talking about here, refreshing, because I'm explaining tREFI. The first step is to pre-charge this bit line to right around 0.5 volts. Why does it do that? So that it can detect the change in capacitance. So this bit line is now carrying 0.5 volts. But we've closed this transistor because the word line has been asserted, and part of that 1 volt is leaking over here and hitting this bit line. So this 0.5 volts is increasing, and that increase is being detected by something called a sense amplifier. I don't feel like writing it all out. Sense amplifier right here. And that sense amplifier has detected that this 0.5 volts is increasing because this 1 volt that the capacitor was holding is discharging into the bit line. When the sense amplifier detects that, it shoves more voltage, it shoves enough voltage to account for that previous leakage. And so this fills back up to 1 volt. Now that is a read-write operation. A refresh is nothing more than a read-write operation. Now, let's go back to this example again, and let's talk about it. 0 volts. Here's your transistor. It's been closed because your word line has been asserted. There you go. And just like the example above, we're connecting to a capacitor. All right. That capacitor held 0 volts. Here's your bit line. And again, it's been pre-charged to 0.5 volts. So what happens here? Well, this is why we pre-charge, right? Because the bit line is pre-charged, the transistor is closed, and now what that means is part of that 0.5 volts is going to be flowing into this capacitor here. Okay, you see it filling up a little bit. And that means that this 0.5 volts has gone down. That change is detected by your sense amplifier. Okay? At this point, the sense amplifier knows that there's less voltage on the bit line. That's how it knows that this capacitor should be storing 0 volts. And then it will initiate effectively a discharge of that capacitor. So the bit of voltage is traveling across the transistor, filling up the capacitor, taking this 0.5 volts down to a lower value. That's detected by the sense amplifier, but this gate is still closed, meaning that this voltage right here, this little bit in the capacitor, can now flow back over the transistor, and that will discharge the capacitor, refreshing it to 0 volts. Now, tREFI is just a refresh, okay? So what happens with tREFI? tREFI is a refresh, and let's make this clear here so that you understand this in the simplest terms. tREFI equals a read plus a write, okay? Which equals a refresh. So, when we're talking about tREFI, what we mean is, let's say I've set my tREFI value to 80,000. Okay. Now there's a formula here for determining how many cycles exactly that is. I don't want to get into it. But by default, this was set to 32,000. I increased it to 80,000, and I'm going to try to push it a little bit higher. But what is it doing? All it's doing is lessening your refresh interval. So, when you're playing around with tREFI, remember that what you're actually doing is decreasing the interval at which the capacitor is refreshed. Now, what does that do? Well, as I just showed you, a refresh is simply successive read-write operation. So if you're refreshing less frequently, your resources are conserved to do what? To do more reads and writes, which is going to help reduce your input delay for gaming. It's why tREFI is very, very important for gaming. Right? If you increase your refresh cycles, then you've got read-write operations on top of read-write operations, and it's going to decrease your bandwidth. Okay, the part of your DRAM reserved for reading and writing and the stuff that helps you in your gameplay. So when people adjust tREFI, all they're doing is decreasing the frequency of refreshes, which again are just read-write operations, so that more of your DRAM resources are reserved for read-write operations. And that's why bumping that number can help you out during gameplay. Now, if you go to Reddit or whatever, they're going to tell you to up that number to the highest that you can make it 250,000 or something. But what happens is then now you're not refreshing, and your capacitors leak, which causes data corruption, which is going to cause glitches and microstuttering in games. Okay, so don't listen to Reddit. Okay, you have to understand what this is. Right? Until you understand it, you don't want to be going around faffing with it. It's not that you could break things or whatever, but you don't really know what you're doing. And that's why you know, on this channel, we explain things. That's the point. We explain things so that you can understand them. So now you have some grasp of tREFI and what it actually does. The reason that I chose to explain tREFI first before explaining any other concept is because in the process of explaining tREFI, you have to be able to explain a whole mess of concepts without which you can't really understand how DRAM operates. So by explaining tREFI, you understand rows, you understand columns, you understand bit lines, word lines, pre-charging, sense amplifiers, and understanding that is critical to understanding this entire DRAM process. But let's take a step back to a more high-level explanation of how DRAM operates. So let me go to my little drawing here, because you guys know I love my crude drawings. I've prepared this a little bit. So let's start with just the physical outline here of RAM modules. You got your channel, that's the place in the motherboard where your DIMM goes into. Here in the orange outline is your actual DIMM stick. Your dual inline memory module, your RAM stick, goes into the channel. In the blue outline are your ranks, so we can see we got dual ranks here. And in the purple inner outline there, you have your actual DRAM chips. So we have 8 chips here in 2 ranks. If we expand on one of those chips, we see these banks of memory cells. Each one of these is a 2D array comprised of billions of memory cells, and a DRAM memory cell is simply a pair, a transistor and a capacitor. And then within any one of those banks, you've got all your rows and columns. This is going to be 65,536 rows, 8,192 columns. You multiply those together, you get around, what is it, like 17 billion? And that's how many memory cells are in a single chip. So if you were to expand here from these bit lines in this crude drawing, you would see, so for example, here's your bit lines, boop, 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 boop. And you know, you got your rows going across, and there's your rows. And then, of course, as we explained when we were talking about tREFI, these go into these bit lines, kind of terminate at your sense amplifier. And again, the tREFI example, why I chose that first is because you can explain all of these things so simply by understanding tREFI. We know what the sense amplifier does. And what I haven't gotten into is where the sense amplifier feeds into this column multiplexer. And the column multiplexer enables the extraction of data from this grid of memory cells. And then from there, we go to your read and write drivers. So here, and this again is your column, your 8-bit, your 10-bit column address that tells you where the column is, and that column information is separated in 8 bits, and then it goes to your read driver or your write driver, right? Actually, technically, in modern DRAM, what happens in between the column multiplexer and the 8 bits from the columns going into your read and write driver is a 128-bit buffer, and that enables you to collect lots of different 8-bit column drivers, as long as they're 8 bits from the columns, as long as they're kind of close together. You can sort of group them together in this 128-bit buffer. But for the sake of simplicity, let's say the column multiplexer feeds into these read and write drivers. And again, that's the 10 bits from the column address. So right here, this is the 31-bit address that you would receive from the memory controller of the CPU. The first 5 bits are going to tell you where your bank group and your bank is. So that's this guy here, where exactly you're going there. And from there you have to find the row, which is what these subsequent 16 bits are for. They're going to give you the row address. And from there, all you have are the 10 bits left, and those give you your column address. So when we talked about the rows and the columns. Now, it's important to understand that only one row out of those 65,000, only one can be active at a time. So when you are constantly hitting that one row, it increases the time, it increases the efficiency of your memory, because you keep on going back to that one row where your data is, where you already know what the row is, you've already opened it up. That's called a row hit. And that's an important concept to understand. So just to cement it home, let's pick this one blue line as our active row, and let's just sort of draw a red line through that one, and 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 through that one. And this one stays blue, right? So we know this row right here is the active row, and we keep on going back to that row. If we can keep on going back to that row, memory controller doesn't have to address the bank and bank group, doesn't have to address the row because it's already there. So it's only working with the 10-bit column address. If you can keep on hitting that row, that's called a row hit. The more often you can go back to that row, the more efficient and quickly your DRAM is operating. And this leads into a discussion of our primary timings, which I've written out here. So to understand, we have to understand what an active row is in order to understand what these primary timings are doing. Because if you look at, like, let's say these timings right here, 36, 46, 46, 46, 125. Your 36 being your cache latency. So what is your cache latency? Well, it's basically the time between sending requests to that open row and that data becoming available on the data bus. So your cache latency isn't measuring the time it takes for the 16-bit row address to find the actual row. Your cache latency is assuming that the row has been found. Your cache latency is measuring from the row hit until you get the data. That's what the TCL number is. tRCD is the interval from when the row is, so once the row is activated to when a column of that row becomes available. And it's often 2 numbers for read and write, and they're usually the same. TRP is the time it takes to pre-charge the bit lines before opening another row. So it's how long the pre-charge process lasts before the memory controller issues a command to open a different row within that same bank. So that's your TRP, and then finally you have TRAS, which is just the time it takes between activating a row and the subsequent pre-charge. We talked about pre-charge when we talked about tREFI. So in order to open a new row, you need to pre-charge first. So TRAS is just the time it takes between the row being active and the subsequent pre-charge to open another row. So now we understand what these primary timings are. Slight correction about the memory banks and columns and rows. I mentioned before that if you multiply your 65,536 rows by your 8,192 columns, you get 17 billion. That is not true. I made a mistake there. You actually get about 540 million. You multiply that by your 32 banks, and that's where you get your 17 billion. So you get your 17 billion DRAM cells. That is your 17 billion transistor capacitor pairs within one DRAM chip, not within one DRAM bank. So, small correction there. Or rather a large correction, depending on your perspective. So for this video, what we did was run two sets of benchmarks. One on an optimized and tuned system, and the other one running simply Intel optimized defaults. The only difference is that I enabled XMP on the stock configuration on the Intel optimized defaults, and I FAFO'd with my fan curve a little bit. And that was it. Other than that, it was total stock, total defaults. I'm adding one thing here. I'm just going to go ahead and lock my P cores and E cores at 5.6 gigahertz and 4.3 respectively. This is not going to make any effect on your games, on your FPS, on your 1% lows. This is not going to stabilize frame times. This is just a health measure for your system, and it's what everyone should do. You really need to lock your cores. So, and that gets into a different explanation, which has very little to do with this video. I just wanted to show you that really quick. The full process of doing this actually involves one more step, which is right here to adjust this core voltage. When I finish tuning everything, I'm going to turn this into offset mode. And whether it's a plus or a minus offset, I don't know yet. I'm going to wait until I tune all the rest and do the RAM tuning again, and then I'll figure this part out. I'll set an offset, and then I'll choose a load line calibration level. And that is going to enable me to have, really, really good delta, really small delta between my V core when it's at idle and the V core when it throttles down under load. But right now, I just locked my P and E cores just for just for the health of my system, to avoid that single core boost bullshit that causes degradation. But right now, specifically, we want to get into some timings. So here's your primary timings. I'm not going to mess with those because those I did not mess with in the optimized and tuned version where I ran those benchmarks on. They stayed exactly like this. I simply changed the sub timings. So we're going to go down here, and I want to draw your attention to DRAM ref cycle time 2 and DRAM ref cycle time same bank, tRFC2 and tRFC respectively. Now, what these are, this is basically the time between when a refresh is issued and when you can issue a subsequent command, measured in clock cycles. That's all this is. That's all tRFC is. Now, tRFC2, DRAM ref cycle time 2 is basically the same thing, but set over different row groups. So you can program the refresh, the time between refresh interval and subsequent commands across different rows. That's good for certain types of power management and those types of things. But the same bank is the more important number. So when you're tuning this, what you want to do, you want to start off at like 500. And then you want to work your way down as you're running Carhu tests. But I'm not going to do that because, again, what we're doing here is we're replicating the initial optimization to dial in which exact setting is most responsible for stabilizing frame times. So that's what we're doing in this exercise. And since I've already done this tune, I know that 470 is going to be stable. And I know that same bank 370 is going to be stable, and that's all I'm going to change right here. I'm going to exit back into the OS. We're going to run some benchmarks. We're going to see if these changes have had an effect. So the results of playing with tRFC were very, very interesting. I believe that we have accounted for most of the discrepancy we'd originally observed between the stock Intel optimized default system and the tuned and optimized one. Now we're going to adjust a few more things, and bear in mind that when I'm adjusting, I know what's going to be stable because I've already done this. When you are adjusting, if it's your first time, you want to change one of these at a time and not necessarily in the order that I've done them. So one thing that I'd like to call your attention to right now are these two voltages, DRAM VDD and DRAM VDDQ. I adjusted these because I wanted to find something closer to the maximum operating temperature. Now, if you'll recall, my RAM is water blocked, so I can get away with pumping a bit of voltage. I just saw no real point in going above 1.5 volts here, but at XMP, it's 1.45, so we've pumped it up a little bit there to handle some of the changes that we're going to make when we're configuring. I'll explain these voltages in a second, but I want to get to this one now. This is CPU system agent voltage. This is the stock setting, 1.23 volts. What is system agent? System agent, it helps the different parts of your computer's processor, in particular those connected to your RAM, to communicate smoothly and reliably. It's like a traffic cop. It ensures that the data flows efficiently between your cores, the memory controller, the PCIe express lanes, integrated graphics. It's like a traffic cop for all of these voltages. Make sure that everything's running smoothly between them. That's what system agent does. There is a phenomenon that many have observed that I heard called the reverse chip phenomenon. So what's considered fairly stable, and we're going to switch it here to manual mode, and we're just going to put 1.25. I didn't encounter the reverse chip, but essentially what it is that you will find sometimes in certain processors that going below 1.25 is advantageous. So you might be overclocking, tuning, and although it might seem counterintuitive, pumping more voltage into this might actually hurt your performance. So when you find that, you maybe go down to 1.2, and then you might adjust from there to 1.21 or maybe 1.18 or something like that. You might have to go lower to achieve the desired result. So that's a system agent. Before I talk about DRAM VDDQ, I just want to go real quick up here, and I want to go to the CPU VDDQ, which, I guess I'm just now discovering that I had adjusted this a little bit earlier. I've got 1.4 for the memory controller voltage, 1.4 for CPU VDDQ. So what are these? Well, the CPU VDDQ is basically the necessary voltage for the data I/O lines between the memory controller and the RAM. All right, I'll get into this further when I explain DRAM VDDQ because they perform a similar function. And then memory controller voltage, which is often called VDD2 in some motherboard manufacturers. This is the memory controller voltage, which is isolated to only the memory controller's operations as opposed to VDDQ. It supplies the precise voltage that the memory controller needs, and the memory controller then issues commands to the DRAM, such as reads and writes, and it processes responses from the DRAM, and it's VDD2 that ensures that the memory controller can perform these functions. Going back to this tweaker menu now, let me talk about DRAM VDD and DRAM VDDQ. Let's start with DRAM VDDQ. So just as the CPU VDDQ supplies power to the I/O data lines between the memory controller and the RAM, the DRAM's VDDQ supplies power to the I/O lines that are responsible for communicating with the rest of the DRAM circuitry and with the CPU's memory controller. So, and then you have the DRAM VDD, which powers the core logic of the RAM. DRAM VDD. It's the main power line of the DRAM chip. It powers DRAM core array and logic circuits. So what are we talking about? We're talking about the row and column decoders, the sense amplifiers that we talked about before, the timing controllers that govern read-write operations, refresh cycles, error checking. All of this is powered by DRAM VDD voltage. So consider DRAM VDD and DRAM VDDQ and CPU VDD2 and CPU VDDQ. A simple way to understand DRAM VDD and DRAM VDDQ is that the VDDQ, being the I/O voltage, essentially governs communication with the outside world, right? So the CPU VDDQ, which we see in our advanced memory voltage right here, IVR transmitter VDDQ is what ASUS calls them. And you know, if you have a different motherboard, you can just look these up. It's not too difficult to find the different terminologies. But this is a signal integrity voltage. So you're communicating, the CPU here is communicating with the DRAM. This is the I/O communication on the data lines, communicating with the DRAM, essentially communicating with its counterpart. And the DRAM VDDQ voltage is the I/O specific to the DRAM chip that is communicating with the internal circuitry and with the memory controller. So because these are communicating with the outside world, these are signal integrity voltages because they're affected by the noise, the interference, the other distortions during that high-speed communication. So that's why they're signal integrity voltages, because they influence how well the signals withstand those types of noises. Whereas VDD, and in the CPU's case, VDD2, memory controller voltage, concerns core logic, core functions. So the DRAM VDDQ kind of governs the quality of external communications, that is signal integrity, and that's true of the CPU's VDDQ as well. Whereas the VDD and VDD2 for the CPU are vital for the stable operation of the internal logic circuits. So I hope that's a sufficient explanation of system agent voltage, which we changed here, manual to 1.25, which I know is stable and should be for a 14900K, should be fairly stable for whichever 14900K system you're running. But you know, again, as I mentioned, there's a possibility of a reverse chip. DRAM VDD and DRAM VDDQ voltages, which I tuned to 1.48 earlier. Now, how I did this, I should explain. I simply stressed the memory, put a stress test on it, and ran a game, and then watched the temperatures creep up. And I'm trying to stay around 50, sort of like that. But I was well under that temp, and with my memory block, with my water block on the memory, I'm way below 50C, and I just saw no reason to push it further. But this should supply VDD and VDDQ with enough voltage to perform their functions as we gradually increase the loads while we're tuning. So we changed those, we changed system agent, and we changed over here 1.4 apiece to the VDDQ and VDD2 of the CPU. Okay, so back we are in the BIOS, and remember this guy, our old friend tREFI. So here we go, we're going to switch this one up, pump it up a bit. This again is going to decrease the frequency of our refresh cycles, leaving more bandwidth for regular read-write operations, which ostensibly should help us in gaming. This is the only change we're making right now, and now we're going to run some benchmarks. So now we're cooking with gas. Now we know what these refresh timings do. We know all about memory. We know about how DRAM operates. We know about word lines, bit lines. We know the whole shebang. We are armed with knowledge, and we know which adjustments to make to stabilize our frame times. Now let's see what happened when we adjusted tRFC. So first of all, Talos principle, DirectX 11 with this tRFC adjustment. We have significantly lowered the 1% from the initial optimization, although it's actually very close to what it was at stock. These are the stock settings, and you see a around 15% delta, but with much lower average FPS. Remember, in the tuned configuration, we ticked that FPS way up. FPS stayed up with a much lower delta. So we're beating my initial tune. In Vulkan, we took it down all the way to 10%, all the way to 10% delta. Look at that tiny green bar there. You don't even notice it. Compare that to stock Vulkan setting for Talos principle, 30%. We went from 30% of a delta down to only 10. 30%? %. Primarily due to one refresh timing. And we're not done. Metro Exodus Enhanced Edition in DX12. Now, I wanted to show you all of these because there are a few more settings here. Shadow Quality Ultra. Now, this has a ray trace setting, which lets you go normal as the lowest setting. DLSS off. So when I said no ray tracing, okay, I lied. But this one only has the normal setting. You can't turn it off. Okay. So there you get some of these, and full tessellation. So you get a sense of some of these settings. Metro Exodus, DirectX 12, after the tRFC adjustment. Look at that. Look at that delta. Look at these 1% lows. That's like I said. And this is actually close to the original tune because these tRFC settings, tREFI settings were baked into the original tune. So you could see what they do here. Again, you can't have any there's zero chance of microstuttering when you've got that small of a difference between average FPS and 1% lows. About 140 frames per second and a delta of 6%. Bring it over there so you can see it. 6%. Remarkable. That's DX12 after the tRFC adjustment compared to stock. 140 FPS, but almost 40%. Almost 40% delta. Way, way lower 1% lows in the stock configuration. Red Dead Redemption 2 in Vulkan after the tRFC adjustment, about 23%, 24%, 130 FPS. Very nice delta there. In Vulkan compared to stock, about 28%. Not much of a difference there, but a greater difference will be observed later once you see what tREFI does. So that's Vulkan, DirectX 12, 18%. By the way, I noticed consistently with Red Dead Redemption, lower deltas in DirectX 12 than Vulkan. At least on paper, DirectX 12 seemed to perform a little bit better. 18%, 140 FPS. And again, compared to stock, we went from 18%, we went from 37% all the way to 18. Detroit Become Human. Vulkan after the tRFC adjustment. So again, this game, this is a funky one, all right? So really, in this game, what you're really looking for is the actual gameplay. It's hard to test. If I had this whole thing to do over again, I wouldn't have chosen this game. My thinking was that because of the switching between gameplay and cutscene, that would produce a huge delta. I was right about that, but I was thinking that maybe I could fix it somewhat. I did see it go down subsequently once tREFI was adjusted, but not significantly. And that's really not the story with this game. You still want to monitor it for microstuttering. Microstuttering is unpleasant no matter what game you're playing, and I saw no microstuttering in this game with a 45% delta. So that's how weird this game is. Now, we've already talked about tREFI, so we might as well go into those results. Let me just recap really quick. Going from the stock configurations, Talos Principle in DX11 and Vulkan, 30% deltas. Okay? 30% in Vulkan, much, much lower in DX11 with also many, many fewer frames. Metro Exodus DX12, 40%. 40% delta. Red Dead Redemption 2 Vulkan, 30% delta. Red Dead Redemption 2 DX12, 40% delta. And then you have Detroit Become Human, which is a 50% delta. These are all your stock configurations, okay? 15%, maybe a bit of an anomaly there. 30%, 40%, 30%, 40%, 50% delta. After tREFI. Just giving a pass to all the games here. 12%. 7%. I mean, again, look at those 1% lows and look at your average FPS. There's almost no difference. That green bar is your difference. 7%. 4%. 4%. 4%. This is DX12 after the tREFI adjustment in Metro Exodus Enhanced Edition. No difference. There are no 1% lows. Your 1% lows are your average frame rate. 3.5%. Remarkable. Remarkable what these refresh timings do to your frame times. Vulkan after the tREFI adjustment, 24%. From stock at 28, stock 40, right around 40, stock in DX12, Red Dead Redemption, DX12 after the tREFI adjustment, 17%. 17% from 40. Look at those lows. Look at that delta. Look how small it is. Look at those 1%. And a small improvement ticking down to 40% in Detroit Become Human from stock, which was close to 50. So a little improvement there, even though it's not as consequential in this game. So what we saw here was that there were some anomalies, right? So in some games like Talos Principle, a bit of a smoother experience, although with a much lower average frame rate in the DirectX 11 benchmark at stock settings. We improved in FPS there, but the delta widened. So a bit of an anomaly there. Couple little anomalies as we went along. And then once we got to tRFC, we started to see what we might imagine, having had these timings explained to you, what you'd imagine the result would be. And then by the time we got to tREFI, it's across the board improvement and dramatic improvement. Dramatic across the board. So we now know, and we've now shown, that it is the refresh timings in the BIOS, the refresh memory timings that you must adjust to fix your frame times and to guard against microstuttering. So we've done everything that we can do in the BIOS. We have stabilized our frame times. We've eliminated microstuttering. Now it's time to cook to our taste. Now we're going to play with the graphics settings. And Red Dead Redemption 2 is a great way to do that because there are so many graphics settings, and one of them is not ray tracing. The game doesn't have ray tracing. Now, and that's why it's good for our purposes here, but if you were trying to stabilize frame times and you have ray tracing available to you, tick that up to its highest setting if you have the hardware to support it, because ray tracing will stabilize frame times. And if you need a better explanation of why that is, go watch the previous video. Tessellation. Tessellation increases the number of triangles and vertices on top of which your textures are placed. Now, tessellation without displacement mapping doesn't do much, or rather, it creates a unrealistically smooth sort of image where the bricks and walkways and rocks, etc., are almost 2D in comparison with the rest of the scene. Displacement mapping uses a height map to add textures to rocks and bricks, etc. So tessellation is combined with a displacement map in most modern games. In Unigine Benchmark, I think you can decouple those two and you can see what tessellation looks like without a displacement map. It's not a treat to the eyes. Fur quality, I think I was snake bit by Metro Exodus Hairworks. Hairworks is terrible in Metro Exodus. I didn't test it in the enhanced edition, but in the base game, it is god-awful. It will cause stuttering. Get rid of it. So I left fur quality on high as opposed to ultra. Decals are your footprints, your bullet holes, etc. The GPU has to render an additional texture to put those in, but it's the CPU that maintains their logic. So how long is the footprint going to stay there? That's up to the CPU. Left that on ultra. Parallax occlusion mapping is a little bit similar to displacement mapping, except it's using shading rather than height, and it's not tessellation dependent, and it's not terribly resource intensive. Tree quality, game's got a lot of trees, so I ticked that up. Level of detail. Now, this is a very interesting setting for our purposes, stabilizing frame times, eliminating microstutter. Why? Because level of detail applies to settings off in the distance. Okay? Now, if you're rendering those mountaintops, like say in Red Dead Redemption, for example, you've got those snow-capped peaks. They're very beautiful. You can see the detail with total clarity when you're staring at it when it's a distant mountain with these LOD settings turned up. Well, what that does is it eliminates pop-in, because once you get close to the object, those higher resolutions of those that they won't have to pop in anymore because they'll have already been rendered. So that's why you tick up LOD. And that's what, you know, for our purposes. Like if you want the smoothest frame time experience, you can tick up the LOD settings. And so that's why graphic settings are kind of interesting, because you really have to think about how one setting can affect everything else. Multi-sampling, anti-aliasing just for reflections. I left this on ×2. This is the anti-aliasing that you see that's closer to the water effects. You could tick this up to ×8. I don't think it would hurt too much with my graphic settings, but I found that it was kind of unnecessary. So we're going to talk about anti-aliasing. Motion blur, I leave it off because I can't stand it. TAA sharpening. Now, when we increase the LOD, we're introducing a lot of fine lines in the textures that are observable at a distance, like those distant mountains or whatever. And this can introduce a bit of aliasing. So by sharpening the TAA, and we're going to talk about TAA, you can kind of counteract that. Resolution scale, that's kind of, it's sort of like DLSS, you know, in a way, but not quite. Right? So basically with resolution scale, you can, if you set that resolution scale to below 1, then the game renders at a lower than native resolution, and then upscales that image to the display resolution, which improves performance at the cost of image clarity. And if you set the resolution scale above 1, it renders the game at a higher resolution than the display and then downscales it, which improves visual fidelity but is more demanding on your hardware. Water physics quality, it is actually more CPU intensive than GPU intensive and involves real-time calculations of how water should move and interact with objects around it. Water reflection quality, that's more GPU dependent, and it's really cool. Okay, so it's basically like taking a camera and putting it underwater. So what it's doing is it is rendering the scene twice. So it's very GPU, it's very demanding. Once for the player's normal camera view, and then again from the vantage point of the reflection. So it's like the camera underwater, and then it renders a mirrored view, which is projected from underwater out to the water's surface. And that's how that works. Water refraction quality is how objects interact with the effects of water. So light bounces off water onto a rock, stuff like that. Actually, before we get any further, let's go ahead and talk about these anti-aliasing techniques. So there's a couple types of anti-aliasing. One type is upscaling. So that's like sample rate increasing anti-aliasing, like super sample anti-aliasing. These take samples within each pixel and average the results. So I don't think I need to explain aliasing, but basically, like, let's say you render a line. So there's a line, right? And the line is made of pixels. So if it's a horizontal line, you don't notice, but if you change that line diagonal, it's all made of squares. It's all made of little pixels. And if your aliasing is really bad, you notice those jagged edges. So what super sample anti-aliasing will do is it will upscale the around those jagged edges and then downscale and then mesh those two images together, and that will smooth those jagged edges, which it does very, very well, but it applies to the whole frame and it smooths everything, so it can cause some blurriness. Then you've got your multi-sample anti-aliasing, which only increases the number of samples at the geometric edges, which are also known as primitives. primitives. Those are the edges. Do you ever see like game devs, like how they work when they're like at the initial stages? You'll see like that game before there's any textures. You can see the shapes. That's the triangles that I mentioned before. You can see all the triangles. You can see all the vertices. They're like black lines on a white background. That's what we're talking about here. And it at those edges of those primitives, that's where MSAA does its best work. And so you could think like a character swinging a sword. That can cause some aliasing. MSAA will smooth that, but it doesn't work on the textures. It only works on the primitives. So like a chain link fence on top of a low res, layered over a low res background, that could introduce some aliasing that MSAA would not be able to combat because it doesn't work with textures. It just works with those primitives. So then you get into your anti-aliasing that is edge blurring, like post-process anti-aliasing. It works on the frame after it's already been rendered. And I don't really want to get into the types right now. There's FXAA, there's MLAA, and then there's the one that I want to talk about, which is TAA. Basically, FXAA uses contrast, so it scans the frame for the high contrast disparities where two different contrasts are clashing with each other, which is a ripe environment for aliasing, and it smooths those areas. But again, that can smooth the entire frame and cause some blurriness. MLAA uses the logic but applies it to shapes. Morphology stands for morphology something anti-aliasing. Morphological anti-aliasing, MLAA. So it analyzes shapes, morphologies of pixel patterns after the rendering and applies smoothing where it recognizes jagged structures. Now, temporal anti-aliasing, you'll also see it as initialism TSSAA, temporal super sampling anti-aliasing. This works by blending color information from previous frames with the current frame. It's smarter than these other methods. It uses motion vectors to track how the pixels have shifted due to movement. And the goal is to average out inconsistencies over time by using the information from the other frames that it has sampled. And that leads to cleaner, more stable images and eliminates aliasing. However, this process, TAA, relies heavily on the accuracy of motion vectors, which aren't necessarily always accurate. So that can cause problems. And then when the motion vectors are inaccurate, several scenarios can introduce ghosting. So in the early versions of TAA, you had a lot of ghosting. So rapid object movement can introduce some problems as well to that and cause ghost trails. So that's a little bit of a primer on TAA, on these anti-aliasing techniques. Talked about motion blur, resolution scale, water, physics, quality. So let's get into now full resolution, screen space, ambient occlusion. Let's just explain ambient occlusion at first. So ambient occlusion is a really, really, really cool technology. I mean, it's just so cool. So let's imagine, I have to look at myself. Let me bring my OBS up. So I got a light right here. See where my hand is? Let's put it over here. I got a light kind of behind me, and that it's the sun or something, and it casts a shadow, right? So you'll see the shadow like being cast over here, like as the light sort of hits the back of my neck and casts a big long shadow. So your core game engine casts that shadow because the sun there, that's the core lighting, Okay, so when we're talking about ambient occlusion, we're not talking about core lighting. We're not talking about lighting at all. We're not talking about shading at all. It's more nuanced than that. We're talking a little bit about shading, but it's really nuanced, okay? It's a nuanced kind of thing. So in that example, the sun's back here, the big long shadow is being cast out here. That's your game core lighting that's doing that. But what about this little shadow right here over this eye? So I've got my eye socket and it casts a little bit of a shadow over my cheek. What does that? Well, it's not the core lighting. The core lighting is only giving you that shadow that comes, that the sun is casting across the back of my neck. So that's not that. Speaking of core lighting, by the way, I got like no light on me. Okay, so it's not casting that shadow. Oh, that's too bright. I'll just have to be a little bit dark here. So it's not casting that shadow. That's the core lighting. So what casts this little shadow on my eye? Well, that's what screen space ambient occlusion can do. So, and how it does it, what it does is it takes every pixel and it makes every pixel shoot out a kind of a ray, okay? A detection ray. And that ray detects objects that are close to it within that same space. And so it shoots out this light, it's invisible, right? It's not really a light, but it shoots out this ray, I guess. And that ray will hit a space or hit a texture that's close to it, and maybe that texture will block out the light from the light source, right? So then it knows which objects near it are shaded. And if it puts that ray out and it doesn't see any blockage, then it knows that it's still illuminated, right? But if it detects objects close within the texture, then it knows that it has to shade something. So these finer shadows are made by screen space ambient occlusion. But this setting, there's another SSAO setting in these graphics options, but the full resolution one, what it does is it renders that shader map that SSAO produces in the native resolution, which is unnecessary. There's no reason to do that. I mean, one reason that SSAO is so cool is because it does what it does without a huge performance hit, because it renders that shader map at like a quarter of the native resolution and then sort of imposes that map onto the native frame, onto the native image, onto the native resolution. It sort of upscales it in a sense. It just puts it right on top because you really don't notice the difference. But if you don't notice the difference, you certainly don't need to render SSAO's shader map in full resolution, in native resolution. Makes no sense to do that, so I turned it off. Other shadows, long shadows. Long shadows. I just think they're cool. That's it. I turned them on. They're cool, like for westerns and stuff. Long shadows are cool. Soft shadows mean the rounding the edges on the shadows so that your shadows don't appear pixelated. Set that to ultra. Grass shadows is high instead of ultra on my settings because grass shadows actually are quite resource demanding because you're casting a shadow for every single blade of grass. Particle lighting quality. Now this refers to the overall complexity of the number of particles effects rendered in the game. So it controls it controls. I'm sorry, excuse me. Let me rephrase that. It's about how light affects the particles. So particles like, I don't know, you kick a fire and these little bits of flame bounce up. So this is the way the lighting affects the particle quality. Particle quality is the actual flames that kick up. So that's a different setting, right? Okay, unlocked volumetric ray march resolution. So in a way, it's a little bit like SSAO in that it uses rays in a sense. Okay, but it's very different. But in that sense, it's kind of similar. So this directly affects the resolution at which volumetric effects are rendered. Volumetric effects are things like fog, little shafts of light. Certain atmospheric elements are known as volumetric effects. And how ray march resolution affects them is by shooting out a kind of array that you don't see, but it gathers information, sort of in the way SSO's rays do. And it gathers information based on the way this fog and this little lighting hits these rays, and then it renders them. It sort of renders based on... So these effects are already there. The fog's already there. Okay, the lighting is already there. But the ray marching gathers information about these effects' interaction with the environment, and then it renders them at a far more detailed way. It's basically a way of recording the impact that the volumetric effects have on the scene and then rendering them. Okay. I turn it off, but I might turn it on. Volumetric lighting quality. Okay, so now you know what volumetric effects are. Volumetric lighting quality is just the fog, the beams of light, the quality of these lighting effects. Volumetric resolutions, that's the resolution at which these volumetric effects are rendered. And it's near and far. So the near volumetric resolution, you're going to notice this stuff when it's near. But since it's fog and stuff like little rays of light, you don't notice it so much as at a distance, so that the far volumetric resolution isn't set as high. Graphics API, Vulkan. I used Vulkan for this because I just liked the way it felt. It just felt smoother. And I'm going to share some of those findings with you. But I really liked the way that Vulkan felt. It felt smoother. As far as the deltas, they were higher in Vulkan. They were actually like 23% and about 18% for the DirectX 12. But I just found that Vulkan was smoother. So again, you just sort of cook to your taste. What's next? Vulkan gives you a brightness calibration setting. DirectX 12 gives you a HDR setting here. So you can tune that, calibrate it. MSAA we talked about, FXAA we talked about, TAA we talked about. I left DLSS off. I actually cannot run DLSS at the same time as TAA. So we might try these settings with DLSS at maybe a balanced or quality mode instead of TAA. See what that does. Tessellation quality, again, it's ultra. Lots of little triangles for the displacement map to work on. Particle quality, we talked about the particles. Volumetrics, we talked about. Water, we talked about. Mirror quality, yeah, sure, why not? Now, screen space ambient occlusion, we already talked about. This is the actual setting that you want to turn on. Shadow quality and far shadow quality. This is kind of how I think about near and far. I don't see the far away as much. Why devote as many resources to the far shadows? Global illumination deserves some time. So global illumination is it refers to the simulations that calculate not just direct lighting, like the sunlight beaming through a window, but also the way the light reflects, the way it scatters, the way it diffuses off surfaces, the indirect illumination of other areas, how the light bounces. That's global illumination. Okay. Lighting quality. Now that is your core lighting. Anisotropic filtering. Let's talk about this for just a second. Anisotropic filtering tells the pixel to sample the texture it's a part of more than once. So a pixel is a part of a given texture. Now, if I'm looking at something head on, if my character's looking at something head on, it doesn't need to be sampled more than once. I'm looking at it head on. What does anisotropic filtering do? It's for objects that are viewed far away, objects that are viewed obliquely. If I'm looking at a mountain, it only needs to be rendered. It only needs to be sampled that one time because I'm looking at it. There's the mountain. Okay, so then I walk up the mountain. Now I have mountain banks, parts of the mountain that are disappearing in my periphery. I still want to be able to see them. I want to be able to see them clearly. If I turn my head abruptly to look at them, I want them to be right there. I don't want them to take the time and render again, right? So anisotropic filtering allows me to see that image clearly. And even though I'm looking at it obliquely, it clarifies my peripheral vision, my character's peripheral vision in games. And how is it able to do that? By sampling the texture that every pixel samples 2 times, 4 times, 8 times, 16 times the texture that it's a part of, so that it understands the shape of it, so that it can render it so that the game could render the texture very, very clearly, even when it's appearing obliquely outside of the character's view. It does that by sampling. The 2 times, the 4 times, 8 times, 16 times refer to how many times the pixel is sampling the texture. It does not refer to how far out it goes. That's a misconception some people have. Although anisotropic filtering will help you see objects that are far off in the distance with great clarity, again, because of the sampling per pixel. So that's anisotropic filtering. Texture quality, I think, is pretty self-explanatory. That's the textures that go on top of your vertices and triangles. These are not really graphic settings. Triple buffering. So triple buffering is only useful for VSync and only useful in a certain type of VSync scenario where the GPU cannot render enough frames to match the monitor's refresh rate. So it's trying to catch up to the monitor's refresh rate. That's where triple buffering would be useful, because it doesn't have the display yet to put the frame on, so it needs a buffer. So we create a buffer between the rendered frame, because traditionally we render 2 frames are rendered. One is rendered by the GPU, right? And one is displayed, right, on the monitor, displayed on the output. And so this triple buffering introduces a frame in between, so that the GPU has a place to put the frame, so it's not constantly trying to catch up with the monitor, right? With the refresh rate of the monitor. And doing that enables your VSync to be, to be more effective, right? The GPU won't fall behind because it will have a place to put the rendered frame, but it's useless in my scenario because I don't have VSync on, and it's useless in any VSync scenario where it's the inverse of that situation, where the GPU is outputting a lot of frames, way more than the monitor can handle, and the monitor through VSync accounts for that by simply taking those frames and turning them into capping them at the monitor's refresh rate. All right. In such a case, you don't need triple buffering either. It's not going to do anything for you. But what it will do is introduce negative consequences if I have it enabled, like in this use case here, because by adding additional frames to the pipeline, there are now delays. It's adding another frame. There's now a delay between when the frame is rendered and when the frame is displayed, which can introduce input lag. So we leave that one off. NVIDIA Reflex low latency. So typically, when a GPU is running around like 98%, the render queue from the CPU backs up. And when that happens, you're introducing input lag because CPU is sending instructions that have to wait to be processed. And so you can cap frame rates to solve this. But let's say you're playing a competitive title, you want to render as much as you can. You don't want to cap your frame rates. But you also don't want the input lag. So low latency acts like a frame cap without the downside. It synchronizes CPU and GPU operations so that the CPU is only providing what the GPU can render when it can render it. So there is a kind of a downside here for our goal, which is to eliminate microstutters and stabilize frame times. There is no render queue, right? The CPU is rendering something and the GPU just snatches it. It will only supply what the GPU can use right then and there. It's a synchronized operation. And it's a very, very cool technology. But without a render queue, you will notice every single setting that could possibly introduce stutter. Why? Because there's no buffer. So the latency is slashed, but it removes the buffer that had previously smoothed over these kind of temporal hitches. So this is something that I noticed because I played with this and I turned low latency on in this game, in Red Dead Redemption, where you really don't need it. It's not the type of game where you really need it. And there was some stuttering despite all the work we've done. There was a little bit of hitching. There were a few little bumps on my Frametime graph that I hate to see. And that can happen as a result of this tech because you've eliminated your render queue. There's no queue to hide or smooth out the inconsistencies. So you get stutters. Now, there weren't really any stutters because of all the work we've done, but there were bumps. And there were just little bumps, nothing, no dramatic frame time spikes, no real microstutters, no real hitches like that. But when you're like me and you're really, really sensitive to microstutter, you notice absolutely everything, okay? I want to show you now the graphs of the Red Dead Redemption tests that I ran with these settings that I just showed you. So let's start with DirectX 12. In DirectX 12, I'm getting an 18% delta. That's delta between 1% lows and average FPS. 18% is very, very good. But this is after just tREFI before these settings. It's 17%. So we actually made it slightly worse, didn't we? Not enough that you'd notice. They're the same. All right. Let me drive the point home in Vulkan. Okay, this is the Vulkan benchmark after these graphic settings that I just showed you. 23%. This is the Vulkan benchmark prior to these settings, just with tREFI adjusted. 23%. Graphic settings don't do shit. You want to eliminate microstutter? You got to get into the BIOS. Graphic settings don't do a fucking thing. Windows tweaks don't do a fucking thing. There's lots of people out there who will take your money, who will try to convince you that the answer's in the Windows tweak. Oh, here's a Windows. And I got this registry setting for you. I got this registry tweak for you, boy. This one's going to knock your socks off. Oh my God, you'll never have another microstutter. You just wait. I got the secret sauce for you. And they will take your money. There's only one way to stabilize your frame times. You got to get into the BIOS. I showed you right here, clear as the summer sun, on a system that is not even optimized. Not optimized. That wasn't a full optimization in tune. I changed a couple settings, and then I changed my refresh timings, my tRFC and my tREFI. And I didn't even blow them up. 80,000 it's sitting at. Okay? I can push it much further. Same with tRFC. tRFC2 at 470, tRFC at 370. That's nothing. And you saw what it did. Those are just the refresh timings. That's the BIOS. You got to do some things before you get to that. All right? You got to make sure your memory is stable. You got to Carhu test it for 24 hours. You got to make sure that your timings are stable, including those ones. You got a Carhu test. I didn't show you that part because I've already done that, because I already know those numbers will work. So I was getting back to the original optimization, and I didn't have to get very far until we hit on the timing that does all the damage. We got to the money shot with the tRFC and the tREFI. It took some work to get there. You got to get your hands dirty. You got to get into the BIOS. Okay. This right here, I showed you these settings. I showed you these game settings. They're very, very important because there are edge cases, right? Like, for example, how LOD, how those distance settings can actually help you with your frame times. And you could very easily introduce graphic settings that hurt your frame times. So yes, your graphic settings are important, but once you've already dialed in your refresh timings, these don't mean much. They mean only something to you. In other words, I showed you how to optimize your graphic settings for your taste. That's why I talked about every single one of these graphic settings. So you can decide what works for you based on your hardware, based on the desired experience. That's all for you, and you need to know it. You need to know all of those settings for that reason. But it's not the same as optimization. It's not the same as tuning. It will not stabilize your frame times. You cannot do that with graphic settings alone, or Windows tweaks alone, or this or that. I don't know why everybody is so afraid of the BIOS. Get in there, get your hands dirty, and play. And I promise you, you will enjoy the result. The upshot will be an experience that has you fallen in love with gaming. So the premise of this video was fix your microstutters. I've shown you how to do that. We now know which timings are most responsible for stabilizing frame times, and we established in previous videos why stabilizing frame times fixes microstutters. But that doesn't mean that we don't have some anomalistic findings here. There are some strange things. For example, what was wrong with my initial tune? Okay, so I tuned my system fully with all sorts of subtimings, all sorts of different. I made all sorts of different adjustments. I have books full of notes on everything I did. I was thinking about including some of those subtimings in this video, but I didn't get to it because we discovered too quickly the importance of the refresh timings in the BIOS, those refresh settings, and therefore I didn't need to continue rebuilding the old tune to discover which settings were most impactful for Frametimes, because we discovered them pretty quickly. But there's something wrong with that initial tune, because I got better results with simply getting as far as tREFI, adjusting this one. So there's something wrong with the initial tune. Don't quite know what it is, although we've established that the tRFC and tREFI are the most impactful for balancing those frame times. And I mean stable, baby. I mean, those frame times are so flat. When I play these games, my God, it's so beautiful. I mean, you could rest a golf ball on my frame time graphs. They are fucking tits, dude. Tits. I mean, you cannot do better than this. This is maxing out with the stablest frame times, the smoothest experience, whatever fucking game you play. I mean, it's incredible. You know, this is the upshot of hard work. You get into that BIOS. I mean, we're playing, but it's still hard work, right? But in any event, we still have some anomalies. There are still some issues, right? Like, I've got to figure out what was wrong with that initial tune. I also want to dive more into how these games play with memory differently. So, for example, in Metro Exodus, I know there's a lot of draw calls. It's very sensitive to read writes. And so when you increase the interval of decrease the interval of refreshes and free more memory bandwidth up just for read-write operations, the game is very sensitive to that. The game responds very well to that. Talos Principle, not quite as much. Why? Because Talos Principle is a different kind of game. Talos Principle relies on these managed heaps of memory. So it basically has like a pre-configured heap of memories. It says to the GPU, you're going to use this. Here's what you're going to use. And so that frees it up. That frees the game up to not have to draw from memory for, every single little thing. It already has this managed heap to work with. So it's less sensitive to those read writes bandwidth being freed up by the lack of refreshes, or by the increased interval of refreshes. So these are just sort of things to find out, things to learn about. But I gotta say, what a pleasure doing this project was. I mean, we're talking about one stretch I stayed up for 2 days doing this current stretch that I'm on right now, it's been 24 hours. But what a pleasure it is. What a pleasure it is to have this stuff, this equipment, this hardware, to have my toys and to just play with them, because that's what it's about. You can watch 1,000 hardware unboxed reviews and GN reviews, and that's fine. There's nothing wrong with that, but you will not learn a fraction of what you will learn playing with this stuff yourself and testing it. When I started this channel, I was worried. I thought, I don't know enough. You got all these big guys in this hardware space, and they all know so much, and they know so much more than I do. And just test the shit yourself. Just test it yourself. Don't be afraid to test. Don't be afraid to make mistakes. And when you make mistakes, make a video about your mistakes. Because this is fun. This is our hobby. We get this stuff, this equipment, these graphics cards, these CPUs. We get to play these games. We get to play. We get to tinker. And we get to talk about our hobby. And that is the joy of tech. There's so much joy in this, and it fuels me. It's why I'm up here after 24 hours of doing this. It's why I've stayed up for a total of like 4 days doing this. It's why all my free time is devoted to doing this, because it brings me so much joy. And what you can find out about your hardware just from playing, I mean, words can't describe. Words can't describe what you can learn just from playing. So much more than you can watching videos. And I want you to watch my videos, obviously, but I also want to encourage you to test this yourself. Because every video I've done so far, there's been some discovery that I've made that has shattered my understanding and expanded upon it and expanded upon my knowledge base. I have learned more making 4 videos than I have learned having done this for years and years beforehand. So that's what I wanted to share right now, because that's why I started this channel. I started this channel to share the joy of tech. And my message for all of you is play, test, play, benchmark if you want to. Play with your shit, test it and find out. FAFO, have fun. That's the joy of tech. That's why I started this channel. That's the meaning of Wunyo. And that's the meaning of Wunyo Tech. I'm Dave. Please like and subscribe if you've enjoyed this content. Stay tuned for the next one.